Hi, this is Gabriel Chen, and this is Lab 2 on drag forces. The purpose of this lab is to observe how the momentum principle works when there are multiple forces affecting the object's motion. This is examined through observing how an opposing drag force impacts a falling object's motion. By using a lightweight object easily affected by the drag force and air resistance, the effects of a non-constant opposing force to the constant gravitational force should be made evident. To easily observe this, I compared the observational data from tracking a falling origami rose with two computational models, one that accounted for drag and one that did not. Here is a recording of my observed experiment where I dropped an origami rose alongside a picture of the tracker model. Next to it, above it, is the graphed data. Here we see the EXP position, which is the computational model without drag position, which is the computational model with drag, and observed position, which is our observed experiment. All the models had a roughly polynomial shaped curve, but predictably, the observed model and the drag model curved more gradually and did not fall as far as the computational model and did not account for drag. This is suspected since the opposing drag force should increase as the object decelerates to the ground due to the gravitational force, causing the object acceleration to decrease over time. This deceleration occurs because the drag force is dependent on instantaneous velocity, and the magnitude of velocity increases so long as the net force is still in the direction of the Earth. So the drag force will continue to increase until net force is zero. This decrease in acceleration as time goes on predicts a time where the two forces reach an equilibrium state with constant velocity. This state of constant velocity is also known as terminal velocity. This terminal velocity depends only on the gravitational force and the drag equation. As such, the terminal velocity will remain constant even if the object is given a non-zero initial velocity. In fact, the object will still return to terminal velocity if the initial velocity was greater than terminal velocity, as the drag force will become greater in the magnitude than the gravitational force, causing the object to decelerate to the equilibrium state. If we increase the time frame of our computational model with drag and gave the observed model more room to fall, you will see the graphs become linear when they reach terminal velocity since it is constant. We do not see this effect in the model without a drag force, as there is no opposing force to bring acceleration and net force to zero. While the drag model and the observed model were very closely intertwined, with many overlapping areas, there are small discrepancies throughout. I believe this to be caused by the sway induced by the shape of the origami rose. As seen in the tracker video, the rose does not stay aligned with the y-axis at all times, and this additional air resistance would account for how the observed model falls slower than the computational drag model towards the initial time of release. In future experiments, objects with a more uniform shape like a parachute could be used to minimize the amount of side-to-side movement experienced, and thus keep the net force all along one axis of movement instead of two. Here we have our data and observations. So we have our paper's mass, which is 1.5 grams or 0.0015 kilograms, our gravity, our drag coefficient, our initial velocity, and our initial position. This is the code for my no drag model. On line 35, I have set my ball's mass to 0.0015 kilograms, and I set my initial conditions of position and velocity to 0 on line 38 and 39. Line 43 have a time step, and line 48 have a gravity. At line 54, the drag constant has been set to 0 to account for 0 drag. Line 72 and 74 are our normal update formulas with F net over ball mass equaling acceleration times delta t to give us our new velocities, and our ball velocity times the time step to give our new ball position or change in ball position. And then after that, we have our plotting equations like normal. This is my code for the drag model. The major difference here is line 54, where I have b set to 0.00042, and on line 68 and 69, I have set up equations for the two forces. 68 is weight, where it is the ball's mass times gravity times the position, the direction vector. And then line 69 is our drag force equation, where we use the proportionality constant, drag constant, multiplied by the ball's velocities squared, and then multiplied by the direction vector except in the opposite direction. And then I combine these two in Fnet with W plus Fd, weight plus drag force, and line 70. And then we have our usual update position equations as well, line 74 and 76. And then to find the B, it was a matter of aligning the end position that we found in the observed experiment with the computational results we got here. So it's a lot of fiddling with the proportionality constant. Through these procedures, we were able to confirm how the net force was affected by an opposing non-constant drag force.